Oh, I totally forgot. I didn't upload the video yesterday. I will do that today. All right, these are the new pens, Expo brand. So hopefully we'll see how it goes. There, it came like 8 different colors, but all the colors are not showing very well. So we're going to talk about aromatic chemistry. Aromatic molecules and chemistry. That means reaction of aromatic molecules. But before we get that, let's do a very, very, very fast survey, like review, not survey. What are we talking about? We'll talk about the rules here. We're going to kind of like revisit the rules. But before we do that, let's look at a molecule and see what it is. Okay. So let's look at this molecule. Okay. You know what? Let's change the color. Okay. So this molecule, let's number it 1. And let's have another molecule. Oops, making the same mistake. Okay, this is molecule number 2. Okay. As we analyze and kind of dissect these molecules, we're going to write down the rules of aromaticity again. Okay, molecule number 1. We're talking about whether the molecules are aromatic or not aromatic. Molecule number 1. Don't use the chat too much. Yeah, I think who is that? Jacqueline. Yeah, I think there is a message on the chat, like stereochemistry wise, it's like the medicine that we talked about. Exactly. So right on. We'll get back to it most likely on Thursday. Okay, molecule number 1. So as we start analyzing the molecule for the fact whether it's aromatic or not, how do we go about it? What do we look for first? Speak up. What do we look for? The rules?
If it's cyclo?
Whether it's cyclic or not. Okay. Is it cyclic? Is it a cycle? It's a round molecule?
Yes.
Yes. Okay. Rule number 1 is good. Rule number 2. What's rule number 2?
Alternating double bond?
Alternating double bond. That's Renee. Yeah, I know your voice now. You can't hide, you can't run. Alternating double bonds. I'm really, like shorthanding because to save space and save time. So just, if you don't understand, just give me a holler. Alternating double bonds, it has alternating double bonds, but there is a little problem here. But is it really a big problem like a sigma wall problem? Yes or no?
No.
No. It's not a sigma wall problem. Okay. And then the next point is carbocation may be okay. Carb anion may be okay. Or lone pair may be okay. So this guy has an element nitrogen with a lone pair. So does this guy. Okay, we'll go to molecule 2 in a second. So it's got a lone pair. So the next question, so it may be okay, it may be aromatic. So the last concern is, I think we checked yesterday, the purple color kind of shows well. So the last concern is, what do you check at the very end before you make the call that it's aromatic or not aromatic? What do you check at the very end? What's that?
Labile electrons.
Number of labile, that means not stationary. Number of labile electrons, we try to write it as 4n plus 2. Okay? And if we can, then it's good. If we cannot, then it's not good. Okay? N has to be a whole integer, full number. 1, 2, 3, 4, 5, 6, 7, 8, whatever, including 0. So what do you think the number, the labile electron number is for this molecule? Should we count the lone pair or should we not count the lone pair? What's the rule there?
Yes, because of the sp3 hybridization.
It's sp3 hybridization. Therefore, we count. So therefore the number is 1, 2, 3, 4, 5, 6, 7, 8, 6, right? 1, 2, 3, 4, 5, 6. Therefore, this is aromatic. Molecule number 2, cyclic, alternating double bonds, double, single, double, single, double, single, right? Looks good. Whether we like it or not, it has alternating double bonds. So rule number 1 and rule number 2 are satisfied, but at one corner of the hexagon, there is a lone pair. Should we count that lone pair? Yes or no?
No.
No.
No. Jihad, why should we not count the lone pair? Because what kind of hybridization does nitrogen?
sp2.
So the number of electrons here is also 6. Good. Okay. All right. Next molecule. Next molecule is something that we haven't done yet. We haven't worked on yet. Molecule number 3. Okay, you need to be really comfortable with what we have learned in the past. If you forget how many electrons does oxygen have in its outermost shell, if you stumble upon those concepts, then you're going to be in trouble. This is why, cruising through organic chemistry is easy, provided you remember what happened in the past. Okay, if you don't remember your past chapters, cruising through chapter 6, 7, 8 may be difficult. So you need to know, if you're confused, like, why did he write a lone pair on the nitrogen, but when there is a carbon, there is no such thing, but you write a hydrogen. If you're confused about that, you are in trouble. You need to be really on top of it. So 1s2, 2s2, 2p3, 1s2, 2s2, 2p4, 1s2, 2s2, 2p5 would be fluorine, 1 extra electron, 1s2, 2s2, 2p6 will be neon. You need to be on top of it. Okay, so what's the deal here for this molecule? Cyclic?
Yes.
Alternate double bond? Well, alternate double, single, double, single, double, single, but there is a problem. It kind of looks like sigma wall, but not really sigma wall, but it's got a lone pair, but the problem is it's got 2 lone pairs. Okay, so how do we do the counting? You count 1, 2, 3, 4. So should the number be 6 or 8? Should you count both lone pairs or should you count only one lone pair? Can somebody come up with a plan, like how do you justify your answer? one lone pair or two lone pairs, and then you have to kind of justify, like articulate why. I'll give you 15 seconds to think about it. Unfortunately, we can discuss out loud. You can speak out. You can think out loud, and I really don't mind. I'll be
What was
happy.
the question again?
Sorry.
What was the question again?
The question is, what's the number of labile electron? 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6, 7, 8? What's
I
the
think
number
it's
of electrons? Should you count both lone pairs or only one lone pair? That's the question.
I think it's both.
Rene says both. If that's the case, then it's not aromatic. If this is the case, then it's yes, aromatic. What do you guys think? I use that example of monkeys sitting on poles, and one pole has a kind of a bifurcation, looks like a Y, okay? So there are poles, and usually the monkeys run around the poles, right? 6 monkeys or whatever number of monkeys. But one pole has a shape like a Y, and there are 2 monkeys. Think about it like 2 lone pairs or 2 pi electrons, okay? Can both monkeys participate in the running around business, the monkey business, or only one of them can participate at a time? What is your answer for that question? Silence.
Both?
Both can run. So there is a pole here. Okay. There is a pole here. Usually there are poles like this, right? And the monkeys are jumping one from green to the blue, blue to the red, red to the yellow, yellow to the whatever, right? But then in this case, one pole looks like this, and there are 2 monkeys sitting on the blue and on the green, and there is a red. Can both of them, can both lone pairs participate at the same time and jump to the next carbon? Can both
No.
be flowing into a direction, or will that create a lot of crowding? What's
I
your
think
gut?
it's going to create a lot, like it's going to be crowded. So no, I don't think so. Like if you put it as a monkey, one monkey falls down.
See, that's why I like the example of monkeys. Yeah, both monkeys cannot jump onto the same pole, one point pole. There are 2 monkeys sitting here. They cannot jump. One guy has to be patient and wait for the other monkey to run to the next pole, and somebody else from the other side can jump into that end of that Y. So the bottom line is both lone pairs cannot participate in the spinning around in the resonance. Only one of them can participate at a time. So you count only one. That means this is not right. This is right. So the number of electrons is 6. This is aromatic. So the bottom line is, if you just want to remember, and if you want to remember like a little trick, the bottom line is if there are 2 lone pairs on the same atom in the corner of an aromatic molecule, you count only one of them. Okay? Clear? No confusion?
Yes.
Okay, Diana, we're good. Okay, so let's analyze a few more molecules. So this is aromatic. We have already seen it. I'm not going to like have you guys work on it. We already know this is benzene and it's aromatic. What about this molecule? No one says that it has to be only one cycle. It can be 2 cycles. 2 cycles fuse together. It's a bicycle. It's actually, I'm not kidding. These molecules are called bicyclic compounds or tricyclic compounds. When you have 3 cycles fused together, this is a bicyclic molecule. This guy is called C6H6 benzene. And this molecule, when you have 2 benzenes kind of stuck together, this is called naphthalene. Benzene is a liquid. And naphthalene is a white solid. And naphthalene has a very interesting property, a physical property. Before I talk about the property, how many of you are there? 36. The number has decreased, probably because I'm posting the videos. What happens if I don't post the videos? Maybe the rest of the class will show up. I'm not that mean. I'm not going to do that. Okay. Naphthalene. It's a commercial product. They come in round, maybe about that size, what I have seen in India, round white balls like spheres, and they're used to keep insects away, like cockroaches and bugs that damage your expensive clothes and stuff like that. So a lot of times in the closet, in the suitcase, in the trunk, where you have your clothes stored, or in boxes, people like moms and aunties and parents in the past, and now we throw those naphthalene spherical things. What's the commercial name for it? Who remembers? Who knows what I'm talking about?
Mothballs?
There you go. It's mothball. Who are you? I can see your picture, but I don't see your name.
Patrice.
Okay, Tris. Thank you. Yeah, that's mothball. Now, what specific physical property does naphthalene or mothball have? Usually, if you take ice, solid state, if you let the ice sit there in a glass, it melts. So solid to liquid, and then the liquid becomes gas or vapor, and it disappears, right, as it goes into atmosphere. So it goes from solid to liquid to gas. If you remember somebody using mothball in your house, and if you come back to that same mothball after like 2 months or a year or 6 months, does the mothball look the same or looks a little different?
It's supposed to be a little bit smaller or like nothing because it turns everything into gas, isn't it?
Chihek, very good. So what he's saying, I don't know if everybody heard, that mothball diminishes in size. That means it's disappearing. I mean, it's not magic. It cannot disappear. No one is going there and shaving off some of the material and throwing it in the trash. It's just disappearing. But do you see any liquid around that naphthalene mothball? No. So that means it's going from solid to gas phase, bypassing the liquid phase. And there is a special term to describe that physical phenomenon when something does not go from solid to liquid to gas, it goes directly from solid to gas. What's that word? It's also used to describe a human personality or like a trait or attribute, like someone who loses temper pretty quickly. You say that guy Shantanu has very this temperament. It's a V word. Who remembers? What's the word? Or the process is an S word. That's also used for describing human beings. What's the V word? The naphthalene is very something. V-O.
Volatile.
Volatile. There you go. Fantastic, Richard. Thank you. Volatile. And the process by which a volatile compound goes from solid to gas, basically disappears. What's that process called?
Is it sublimation?
Sublimation. Thank you, Lara. So this guy is volatile, and the process is called because it sublimes. That means solid to gas, not solid to liquid to gas. It totally bypasses that, okay? And that's pretty important. I think there are some other compounds that I could have been, excited to talk about as aromatic compounds, but I think I'm going to restrict myself and try to control my urge to talk about that because we have very little time left with all this mess and chaos going around. So I'm going to take a picture and let you guys kind of absorb what's written on the board. Pretty much like review. This is review. And now after I erase the board, I'm going to switch to reactions of aromatic compounds. Okay. All right. Any questions? No question is a bad question. All right, doesn't look like you guys have any questions, so let's erase. What do you guys think about these new pens? Better, worse, same?
Yeah, I could see better.
That's what I thought too. It's also easier to erase because it imprints much easier. I don't have to press so hard like the other pens. We should have done it a long time ago. And it's just really easy for me to erase because it's so light. Does it also have like any smell? It's like organic dye, whatever the color they're using, they're resourcing it from. It's not as harmful. It doesn't smell aromatic, actually. It doesn't have any funny smell. It's pretty odorless. All right, so you have seen this chemistry before. You have seen this reaction. You know that aromatic compounds. So all the reactions that we're going to be doing, so I'm just trying to be assuring you that all the chemistry is going to be done on benzene. Thank goodness. We are not going to be using any funny molecule with nitrogen or sulfur or whatever, oxygen, and do the chemistry. We're going to use only benzene. So now we're going to talk about reactions of aromatic compounds. Okay. Let's start with benzene. And the reaction is going to happen to just one double bond of the 3 double bonds in the benzene. So what I'm going to do is I'm going to write out these 2 hydrogens just because things are going to happen on that double bond. You can choose any double bond. You can choose this double bond or this double bond. It really doesn't matter. Now, you have seen in the past that because of that aromatic stability, the special stability of the aromatic system, spinning electrons around the periphery and having the right number of electrons, the molecule is super stable. Even though it looks like a double bond, it looks like like an alkene. It's not really an alkene, and therefore we have dedicated a completely different chapter to discuss this type of molecules. The chapter is aromatic compounds or aromaticity or whatever it is. Okay, so it under normal circumstances you would expect a double bond to react with bromine. This guy doesn't. Under normal circumstances, you would expect a double bond to react with hydrogen gas with a catalyst, hydrogenation reaction. In this guy, the aromatic compounds don't do that. But you have also seen one reaction when we first started discussing aromatic chemistry, like when you treat it with bromine and iron tribromide, as a catalyst. Okay, iron tribromide, this is a catalyst. It's also a Lewis acid. Lewis acid, and it's also a catalyst. Okay, when you take this, when you have this cocktail, when you have this recipe, you add bromine and you add a little bit of iron tribromide. A catalyst doesn't have to be used in large quantity. If you have 1 gram of the benzene and let's say 0.8 gram of bromine, you can just have like a pinch of like few milligrams of iron tribromide, and that will do. Because as it helps the reaction get going, it regenerates itself as the reaction is taking place. It goes through one cycle of catalyzing the reaction, regenerates itself, then again it goes back and helps another molecule convert, then goes back to iron tribromide, and it just keeps on in that cycle, catalytic cycle. So it keeps regenerating itself. So you don't need so much catalyst. You can just use a little bit of catalyst and that's good enough. Okay. So when you do that, it turns out that the molecule undergoes a some kind of a reaction. One of the hydrogen stays and one hydrogen gets replaced with a bromine. Okay, and this reaction, it's under so what happens is this particular cocktail, bromine and iron tribromide, it produces Br plus bromine, like everybody in that series of halogens, fluorine, chlorine, bromine, and iodine. How many electrons does fluorine have in its outermost shell, in its valence shell? How many electrons does it have? Give me a number. 1, 2, 3, 4, 5, 6, 7, 8. One of the 8 numbers.
7.
7. So if fluorine has 7 electrons, chlorine also has 7 electrons, bromine has 7 electrons, and iodine also has 7 electrons. It's the shell level differs. Okay, fluorine has it in its second shell, chlorine has it in its third shell, bromine has it in its fourth shell, and so on and so forth, the fifth shell. Okay, 2, 3, 4, and 5. Fluorine, chlorine, bromine, iodine. So the bottom line is bromine is comfortable and neutral when it has 7 electrons in its outermost shell. In this case, after you throw in iron tribromide and bromine, they react together, and basically what iron tribromide does, it snatches away a bromine from the molecular bromine. Bromine, another bromine is making a molecule, making a bond, covalent bond, by sharing their unpaired electrons, and they feel good. Because iron has electron deficiency, it's kind of like a disease that iron was born with. Okay, that's why it's called Lewis acid. Iron tribromide, aluminum chloride, BH3. Remember boron, BH3, 1 boron and 3 hydrogens, and the boron doesn't have any more electrons. Boron is only born with 3 electrons in its outermost shell. So boron, iron, aluminum, they are all born with 3 electrons in their outermost shell. So they can bond with 3 other guys like this guy, but they have a natural deficiency of electron density. They can use some electron density from somebody else. So when they meet each other, this guy snatches away a bromine from the molecular bromine with the electrons, bonding electrons, leaving out 1 bromine with nothing. So that's how iron tribromide and bromine produces a bromine cation. And this works like an electrophile. Okay, this works like an electrophile, E plus means electrophile. Electrophile means electron loving. Okay, electrophile means electron loving because it's electron deficient. It's looking out for extra electron density. That's why it's an electrophile. If I don't have money, if I'm poor, then I'll be looking for money. I'll be moneyphile or dollarphile. If I like something else, flowers, I'll be a flowerphile. So phile, the word Latin or Greek, it means loving or love or something of that nature. Okay. So the bottom line is benzene or an aromatic compound can react with an electrophile and undergo a reaction which is not, if I ask you three answers. First question is, this reaction is addition. This could be a question in the next quiz or exam. Second answer is, it's a substitution. Third answer is elimination. Fourth answer is none of the above. Which one is the correct answer if I ask you what kind of reaction we just showed?
Substitution.
Substitution? Why, Richard? What substitution means? You're removing something and you're adding something. What are you removing and what are you bringing in?
Removing the hydrogen and bringing in the bromine.
As simple as that. That's it. You're removing that hydrogen and bringing in the bromine. Therefore, the correct answer is it's substitution, right? So this reaction, this specific reaction that we just saw happening on the aromatic molecule, okay, is involving an electrophile, is involving an aromatic compound, and it's a substitution reaction. So you put those three words or three excuse me, concepts together and you come up with a name. So this reaction is called electrophilic aromatic substitution. This reaction is called electrophilic aromatic substitution reaction. As simple as that. So if you ever see a question in the upcoming quiz or in the exam or in the final that I show you a reaction and I ask you what kind of reaction it is, you pick these three words. Electrophilic, because there is an electrophile involved. Aromatic chemistry. It's happening on an aromatic system and it's a substitution. Okay. So what I'm going to do now is, this is going to be the second mechanism that I'm going to be asking you to kind of follow. And I want you to kind of memorize or practice or understand and basically grasp the concept in a generic form. So what I'm going to do is I'm going to show you exactly how this reaction happens by breaking bonds, by moving electrons, by regenerating, breaking aromaticity, by bringing back aromaticity using an E+. Okay, and there are 5 reactions under this category. One is reaction with bromine, this cocktail. This is the number 1, and then there is going to be a number 2, a second reaction. So first reaction is bromination, second reaction is going to be nitration, third reaction is reacting with sulfuric acid and you add an SO3H group. That's called sulfonylation. Sulfonylation, then it's an alkylation. You stick an alkyl group like a methyl, ethyl, propyl, isopropyl to the benzene ring. That's called alkylation, a special name after 2 scientists, Friedel, Kraft, alkylation. And the last reaction is called acylation, Friedel-Crafts acylation. Methyl or an alkyl group and a carbonyl. That whole thing is going to come as an electrophile and get stuck on the benzene ring. And that's a very powerful reaction because you are basically decorating an aromatic molecule, benzene ring, with a bunch of different things. And you can really make awesome chemistry. You can make really pretty and useful and sometimes unuseful molecules using all this chemistry. So electrophilic aromatic substitution reaction, super powerful and extremely helpful for synthetic chemistry, for synthetic purposes, whether you're just trying to understand a phenomenon or you're trying to make a drug or medicine or something agriculturally relevant. It's very, very powerful, okay? So this is the reaction. This was an example and it's a substitution. What we're going to learn now is how this reaction takes place or the mechanism of the reaction, okay? We're going to talk about that here. Mechanism of this reaction, okay? So let's start by drawing this molecule. I'm just going to draw the third double bond in blue, the hydrogens. And all I'm going to do is I'm going to add an electrophile like E+, okay? And the E+ will vary from reaction to reaction. For the first reaction, E+ is Br+. For the second reaction, E+ is NO2+. For the third reaction, E+ is SO3H+. Fourth reaction, E+ is some kind of an alkyl plus, like a carbocation, CH3+, or CH3CH2+, or an isopropyl plus, something like that. For the last reaction, it's going to be alkyl group, let's say methyl, and a carbonyl, and the plus sign on that carbonyl carbon, okay? So Br+, NO2+, SO3H+, alkyl plus, and alkyl CO+. There are five reactions. We're going to show the same mechanism, the generic mechanism by which all of the 5 reactions will take place, okay? It doesn't matter which reaction you're doing. Production of the electrophile is different, maybe, depending upon what the cocktail is, what the recipe is. But once the electrophile forms, it follows this identical procedure or mechanism to make the final product, where the electrophile gets stuck on the benzene ring by kicking out a hydrogen. All right, so when the benzene ring is encountering an electrophile, a powerful electrophile, what happens is one of the double bonds in the system opens up. Either it opens up from hinging itself from the top, or it stays hinged at the bottom and it opens up, right? So this is the first mechanistic arrow. Again, mechanism is nothing but our renderation of how the chemistry might be happening, how the electrons are flowing, how a bond is breaking, then what's happening, then which electron is flowing in which direction, then how does this something gets its neutrality back by losing a proton to a base, all that stuff. That is mechanism on the whole. That is the chemist's best guess to what exactly is happening in the black box. You are throwing in bromine and iron tribromide with benzene, and from the other end, this product, bromobenzene, is coming out. How is it happening? That's our imagination or our best hypothesis, you know, pretty much founded on the evidence. Okay, that happens. As this happens, you basically screw up the aromaticity of the molecule, the benzene ring. Aromaticity is gone temporarily for a very short period of time. The hydrogen is here. This bond has opened up. Okay, it has picked up the electrophile. Electrophile is happy. Electrophile didn't have an X electron. This bromine was missing its electron. Now, after the double bond has reached out to the electrophile and bonded with the electrophile is happy. Now it feels that, I have an electron in my outermost shell, in my valence shell. I'm happy, I'm not positive anymore, I'm neutral. But during this process, the benzene ring kind of got into trouble by losing its aromaticity and generating a positive charge here. Because you can see that you took away this electron from this carbon, okay? This carbon got deprived. So this carbon is positively charged now. But you have accomplished something. You have stuck the electrophile on the aromatic ring. But there are too many things here. So how do you fix the problem? How do you return aromaticity? This is kind of like, you remember in the past how we returned the lone pair on the nitrogen or on the oxygen by bringing in a base and basically plucking a proton? Same deal, same trick. So a base comes in, whatever the base is, let's not talk about it. And we're going to always call a base with an uppercase B with a lone pair. This is your generic base. Whatever base. It could be one of the species in the reaction itself. It is, okay? The lone pair will grab the proton, just the hydrogen. That's why I'm using the word proton. It's going to go away. This is how the bond is going to break. Okay, bond is going to break here, and these electrons will come back in the aromatic system, regenerating the aromaticity of the molecule. Okay. That's it. So this is the mechanism by which an aromatic molecule such as benzene grabs an electrophile, gets into a short-lived intermediate state, which is kind of bad because the aromaticity is gone. It's not good. It's very high energy, okay? But it happens. It goes to this could be very short-lived. It could be like picosecond or nanosecond long. I don't know the kinetics of this reaction, exactly how long this is going to last. It's going to happen, and then base will come and pick up the proton, returning the bond between the carbon and the proton back into the system, regenerating the aromatic system, and thereby accomplishing the substitution reaction. Okay, I'm going to take a 10-second break. I'm going to take the picture, let you guys absorb the material, kind of let it soak in, and then if necessary, we can discuss it. And I'll wrap it up by discussing the rest of the 4 reactions. Can you guys handle it? This is very important, and not just for the next quiz, but it's for the next exam, and it's for the final. Okay, this is very, very important. I'll pause for like 10-15 seconds. You can think out loud. You can ponder. You can make a comment. You can do whatever you want. Looks okay? You can handle it? All right. I'm erasing. All right. So this is the reaction, electrophilic aromatic substitution reaction. And there are 5 of them. So you learned the generic mechanism, okay? Not that difficult. And now we have to talk about the 4 other reactions, and that's pretty much it. And what I'm going to do is I'm going to put the molecule in the middle. Maybe I'll put the molecule up here and do like a star reaction, go in 5 different directions. Yeah, let's do it that way. Yesterday I did it from the middle. It got pretty crowded. I didn't like how I did it. Okay, so I'm going to use the 5 colors. All right, so now we have benzene. I'm just going to make it all black, except one corner will be a blue hydrogen. That's where the reactions are going to take place. First reaction we have already seen. Bromine and iron tribromide, and it's going to generate okay, it's going to generate bromobenzene. That's the first reaction, and the electrophile in this case is Br plus, and I'm going to circle it using a green color. That's the electrophile in this particular reaction. Second reaction is going to be using nitric acid and a little bit of very strong acid, something that's stronger than H plus. So catalytic H plus, and it's usually sulfuric acid. So you just need a little bit of very strong acid. Nitric acid itself is very strong. Sometimes nitric acid is enough. You don't need this guy. Sometimes people still add a few drops of sulfuric acid in the reaction, and the reaction takes place, and this is what comes out of the reaction. Nitro group. And in this case, the electrophile was NO2 plus. That was your electrophile. Okay. Next reaction, sulfonylation. Let's use the blue color. H2SO4, sulfuric acid, and the product is SO3H, okay? And the electrophile in this reaction happens to be SO3H plus. That's your electrophile for this reaction. Next reaction, alkylation. You stick an alkyl group to the benzene ring, which is pretty cool. How do you do it? Well, you use an R halogen attached to a halogen. This is an alkyl halide. Alkyl halide, okay? Let's use an example. You use an alkyl halide plus a Lewis acid. Okay, that's the cocktail. That's the recipe. And let's use a specific example. Chloroethane. Okay, chloroethane and aluminum trichloride. So chloroethane is your alkyl halide, and aluminum trichloride is your Lewis acid. Okay, why aluminum trichloride is a Lewis acid? Because aluminum is born with 3 electrons in its outermost shell, like iron, like boron. That's why they're missing 2 electrons in their outermost shell, and therefore they're very hungry, they're thirsty for electron density. They're electrophiles too, they themselves are electrophiles, and they kind of act like acid because they can grab electrons from somebody else. They can take somebody else's lone pair, okay? And that's exactly what happens here. This cocktail produces CH3, CH2 plus. It produces like a carbocation. That's going to be the electrophile. And what happens at the end of the day in the reaction? It produces this CH3, CH2 guy gets attached to the benzene ring. So you produce ethyl benzene. In this case, the electrophile looks like this. This is kind of confusing because it looks like a hyphen. So it's in reality, this is what it looks like. Okay, that's your electrophile in this particular case. Okay, so this reaction is called Friedel-Crafts alkylation. I'm going to write that down. Okay, the last reaction involves an alkyl group, then a carbonyl. When we talk about carbonyl chemistry, it'll make more sense. Carbonyl, and then a halogen and a Lewis acid. Okay, let's use some specific examples. Specific example will be, let's say, methyl, carbonyl, chlorine, acetyl chloride. We will discuss it later on. Right now, just imagine that you are dealing with a carbonyl compound, carbon double bond oxygen, an alkyl group, and then a halogen is attached, and you use aluminum trichloride as a Lewis acid. What happens in this reaction? Well, this is also a very powerful reaction. And what ends up happening in the molecule is this. You end up sticking this molecule minus the chlorine, okay? This whole thing gets attached here. And in this case, in this last reaction, the electrophile is...
Who did?
This,
BC?
No way.
you guys can hear me, right?
About that Fullerton said there.
This is your electrophile. Okay. So these are the 5 reactions. This might be looking easy on the board as I'm working on it using different colors, but it may be a little overwhelming. It may be a little complicated. So the generic mechanism is what we have discussed in the previous board, in the previous session. Okay. There are 5 reactions. So let's say if we start from here, let's number this molecule. Let's say this is molecule number 1. This is molecule number 2. This is molecule number 3. This is molecule number 4. This is molecule number 5. This is molecule number 6. Okay? So 1 to 2 is bromination. 1 to 3 is nitration. 1 to 4 is sulfonylation. 1 through 5 is called
Jesus, this guy wrote a lot.
Friedel-Crafts. Okay, you need to remember Friedel-Crafts. F-R-I-E-D-E-L, name of a chemist. C-R-A-F-T. Friedel and Kraft, 2 people. Okay, Friedel-Crafts alkylation. And the last reaction, 1 through 6, is Friedel-Crafts acylation. F-R-I-E-D-E-L-C-R-A-F-T A-C-Y-L-A-T-I-O-N. Okay, I do not know if this is overwhelming, but there is a lot going on this board, and I think we finished a little early today with your class, so I can open up for some discussions, or I can call it a day, because this is where we kind of stopped for the Monday, Wednesday class yesterday. I can just go over it one more time before we call it a day. Benzene reacting with an electrophile. The electrophile looks different. Today, the electrophile could be, it's like a different 4-footed animal. It could be a cat, or a dog, or a fox, or a hyena, or something else, okay? They're different. In this reaction, the electrophile looks like Br+. In this reaction, the electrophile looks like NO2+. In this reaction, the electrophile looks like SO3H+. Where does the SO3H+ come from? It comes from sulfuric acid. Where does the NO2+ come from? NO2+ comes from HNO3, nitric acid, and a little bit of sulfuric acid. In this reaction, the electrophile looks like this. An R group, and a CO, and the positive charges on the carbon. It looks really weird. When I first saw it, trust me, I was very uncomfortable, like, how can that happen? But that happens because there is evidence that we are making this molecule. That means this stuff with a positive charge must be happening, okay? So this stuff happens. So that's the electrophile. For this reaction, when you're taking an alkyl halide, chloroethane, chloromethane, bromopentane, you name it, isobutyl chloride, isopropyl halide, something, iodide, you just take that, throw in some Lewis acid, just a little bit, cook it up for some time, and you work it up, and you see that, oh, something is on the benzene ring, got stuck. And what is that thing that got stuck? Well, that used to be the alkyl part of the alkyl halide. Whatever you use, that got stuck on the benzene ring. So that's another electrophilic aromatic substitution reaction, and the electrophile looks like whatever the alkyl group is, that carbocation is the electrophile. And so these are the 5 different reactions. They can all be called electrophilic aromatic substitution. One of them under that general category, one is a bromination, one is nitration, one is sulfonylation, one is Friedel-Crafts alkylation. Alkylation means you're alkylating. If I undergo alkylation, I'll have an ethyl group stuck here or on my back, like a long octyl group, okay? And then Friedel-Crafts acylation, when you attach something with a C double bond O and something else hanging off of that carbon. Whatever it came as, that same thing is going to be stuck on the benzene ring. Take a look at it. I'm going to take a picture. We are pretty much officially done for the class because I don't want to dump anything else today, since that will make us go more faster, further with respect to the other class. So we are pretty much done. No exam on Thursday. I'm going to send an announcement. And I'm also going to upload the pictures and the videos as soon as I can. Any questions? We have time. you guys need to practice. So what I always say, there is homework. Practice what we are discussing here in this class, in this Zoom online classroom. Whatever we are discussing now, make sure you can do it with your eyes closed. Practice it. If you do not practice it, I can guarantee that unless you're really gifted with organic chemistry, which you may not be, most of you, because this is not your cup of tea in general, okay? You might not hate these lectures, but this is probably not what you have always dreamt of doing, making bonds and breaking bonds, okay? So if you're not, you have to practice. So your job should be just to practice what we are discussing in the classroom, online classroom. Just keep practicing. I'm sending the pictures. The resolution of the video may be not so good, but the pictures I've seen, even though my phone sucks, but the camera is okay. I mean, the resolution is pretty good. So you can probably look at the picture, print it out, or look at it on your cell phone or wherever, and you can run the video, and it'll really make sense. So please, I urge, I beg you to practice so that you can do well in the leftover exams. Okay, I might throw more quizzes and then take off your worst quiz or worst quizzes. If I end up giving you 7 quizzes, I might remove 2 worst scores. So I think it'll do you some good. So I want you guys to stay motivated and not lose your momentum and give your best shot. I'll keep my mouth shut if I can for like 10 seconds, and then we can call it a day. You can
5 and 6 are both Friedel-Crafts alkylation.
No, one is alkylation, the other is acylation. This is a C. This group is called acylium cation. This guy is called acylium cation, and this is an alkyl cation. They are different. One is just R plus, one is R with a carbonyl plus. So they're the different. This is one and this is the other one. Okay, Diana?
Thank you.
No problem. Anybody else? No? Okay, so then what we're going to be doing is it's 9:09 for a change. We have finished a little early, so enjoy your 5-minute vacation. Please study, please practice. There's a lot of chemistry going on here. On Thursday, I might do a little bit of nomenclature, like naming compounds, not that complicated. We're going to just keep our life easy and simple. Bromobenzene, nitrobenzene, ethylbenzene. We are not going to do the naming at this point. We'll do it later on. This is called a benzene sulfonic acid, stuff like that. We might just name some simple molecules and add maybe 2 groups and teach you a few other things maybe for 15 minutes. Then the last 1 hour, we're going to discuss stereochemistry. I'm already a little stressed out. How am I going to do it? How am I going to pull it off? We're going to use a whole bunch of models, which we have used in the past. So I'll probably have a few models already made because I don't want to putz with the models and waste time. So we'll figure it out. So I may spend just 1 hour on stereochemistry and try to give you guys a heads up on stereochemistry. If I don't teach stereochemistry, I will never be able to forgive myself. I'll be very upset with myself. So that's the plan. And then next week we will probably move to a different chapter, nucleophilic substitution reactions. And then we'll talk about carbonyl chemistry, whatever we can, and that will pretty much help us wrap up the semester. Okay. I'm going to move to the front camera. and see if anybody has any questions. If not, then wait for maybe a few more seconds. Yeah. 16, down to 16, down to 15. Okay, I'm ending meeting. Bye. Have a good day, guys. Be safe. We'll see you guys on Thursday.